In the second lecture of Chapter 5, Stereochemistry, we will cover some new concepts, but before we do, however, let us do a quick review. Last lecture we looked at the definition of stereochemistry, which is basically the orientation of atoms in three-dimensional space. And of course we had a special type of stereoisomer that's called enantiomers. And next we looked at the comparison of molecules in 3D. In today's lecture, we will be looking at the nomenclature of chiral or stereogenic molecules. So here's another term for you. Chiral is the same as stereogenic, so they are synonyms. And we will also look at molecules that have more than one chiral standards. More than one. So it gets a little complex here. And then we'll look at how do we resolve enantiomers. Of course, as we said last lecture, enantiomers are different molecules, and a lot of time, especially in the pharmaceutical industry, only one is needed. So sometimes they have to do a separation. Again, for this lecture, you will definitely need your model set. So again, go get your model set and start building your molecules so you can see them in 3D. Let us look first at cyclic molecules with chiral carbons. So don't forget, chiral here is just another term for stereogenic, or a carbon that has 4 different groups around it. Keyword here is 4 different, because if you do not have 4 different groups around a carbon, you won't have enantiomerism. If you have 3 different groups or 2 that are similar, then it's possible that molecules can be the same. So let's look at some in nature. Carbone, well, here's one. We'll learn how to name that in a second. And here's another one. So these are enantiomers of each other. Here the hydrogen is in the back, and here it's in the front. So therefore they are enantiomers of each other. Of course, as you know, carbone has, based on the type enantiomer, one smells like spearmint and the other one smells like mint. Here's another one that's of extreme importance, tolulamide. As you will see in the book, years ago, the FDA looked at these compounds. They were used to cure, to help at least in pregnant women with morning sickness. It turns out that one was very, very bad. It caused gross deformities in babies, whereas its enantiomer actually assisted with morning sickness. So if there was a mixture, there was a problem. And of course, back in the 50s and 60s, we had a lot of incidents that were very unfortunate, and those babies were called tolulamide babies. So if you have time, go on Google and check out tolulamide babies. And it was caused primarily by one enantiomer here that caused the problem. Okay, what we'll do here is we will learn to name enantiomers. We just mentioned that enantiomers are actually different molecules. They're not the same. They look very much the same, but they are different. If they are different molecules, they must have different names. Just like you have the cis and the trans for the geometric isomers, here we'll have different names for enantiomers. So, this naming system was devised by Kahn, Ingold, and Prelog, and it's called the R and S assignments, or absolute configuration. Basically the R and the S assignment. As you can imagine, one enantiomer will be R, labeled as R, and the other enantiomer will be labeled as S. But how do we do that? Here's how it's done. Here's an example. Here's a carbon that I'm highlighting here in red, and it has 4 different groups bonded to that carbon. The first rule is to assign priorities to the atoms that are bonded directly to that carbon. Priorities here are based on atomic number. So it's the same system that you used when you were assigning E and Z nomenclature for the alkenes. Same system, priorities based on atomic number. So you look at the carbon here and you look at the atom bonded to it. This is chlorine, this is fluorine, this is a carbon, and this is hydrogen. Since chlorine has the highest atomic number, it gets number 1, priority number 1. Fluorine has the next highest atomic number, so get your periodic table and look at these atomic numbers. It is actually 9 for fluorine and actually 17 for chlorine. And carbon, of course, as you know, is 6, so it gets number 3. And hydrogen, as you know, is number 1, or the atomic number is 1, so it gets priority number 4. So let's do that again. So look at the atom that's bonded directly to the carbon. Look at the periodic table and determine the atomic number. The atom with the highest atomic number gets the highest priority. So chlorine here, which is 17, atomic number 17, gets priority number 1. Fluorine, which has atomic number 9, gets priority number 2 because it's next in priority in terms of atomic weight. Carbon, which has the atomic number 6, gets priority number 3. And hydrogen, which has an atomic number of 1, gets the lowest priority number 4. The nomenclature states that we should orient the molecule so that the group of lowest priority is in the back or away from you. Remember, whenever you have the Fisher projection like this is, this group, the fluorine and the hydrogen, are in the back. So in other words, the vertical are in the back and the horizontal are in the front. So the rule states that we need to orient the group of lowest priority in the back. Then we actually trace 1, 2, and 3. So we go 1, 2, and 3. If that direction is clockwise, we assign a R. So again, if it's clockwise, like the clock, going from 1, 2, 3, 4, 5, 6, 7, in that direction, it gets an R. As you can imagine, here's the opposite. So here's the enantiomer. Here's a carbon. Here's priority number 1. Here's priority number 2, fluorine. Here's priority number 3, carbon. And priority number 4, which is in the back based on the Fisher. Okay, so based on the Fisher, the vertical are in the back. So in this case, we go 1, 2, and 3. Notice this direction is counterclockwise. It's going opposite to the clock. If it goes counterclockwise as shown here, it gets a S. So now we can, in fact, give a complete IUPAC name for enantiomers, which would be S or R. So here's a little trick. We said if the group of lowest priority is on the back, you go 1, 2, 3, and if it goes clockwise, it's an R. If it goes counterclockwise, it's an S. But what happens if it's not in the back, as shown here? Because remember, that is a fissure, so the horizontal will be in the front. So what happens if it's in the front? Here's a little trick. If it's in the front, go 1, 2, 3, this would be an R, but the actual assignment would be opposite, which would be S. Okay, so that's just a little trick there. So you can look out for that, but make sure the group of lowest priority is in the back, and then you go clockwise or counterclockwise. If it's not in the back, you go, it's opposite to what you have determined. Okay, let's see if we can apply this information here. So here we have a molecule, and it's 1-bromo-1-chloroethane. 2 carbons, ethane, and this is carbon number 1, so 1-bromo-1-chloro, pardon me, because B comes before C. And here is the same molecule, ethane, 1-bromo-1-chloroethane. But we know that they are different, so they have to have different names. So using the absolute configuration, or another way of stating that is using the R and S assignment, you can see that this will be S, 1-bromo-1-chloroethane, and this will be R. So this is a way of giving specific names to enantiomers. Notice again, if this is an S and this is an R, they are enantiomers. So here's another trick. If you're asked what is the relationship between two molecules, you can determine the absolute configuration. If they're both the same letters, S and S, they are the same molecule. If they are different, R and S, then they are enantiomers. So again, you will have to decide what works best for you. Here is the fissure representation at the bottom for the same molecule. So this is a dashed wedge, and here is the fissure. And notice this is in the back, so you can go 1, 2, 3 and see if it's clockwise or counterclockwise. What you'll get is going to be an S for this one, and this will be the R. Just another quick way of making decisions. You notice that these are mirror images of each other. So this is right across from this, likewise the bromine, likewise the hydrogen, likewise the chlorine. So therefore they are mirror images of each other. Therefore they are enantiomers. Therefore they must have different absolute R and S assignments in terms of the names. So again, whenever you're asked to give the complete IUPAC name, including R and S, you will have to put here R or S based on that absolute assignment. Okay, let us look here at molecules that contain 2 chiral carbons or 2 stereogenic centers. You know where we're going here. It's becoming even a little more complex here. But you'll need your model and you'll need your thinking caps on to visualize these in 3D and then to transform them into 2D and put on paper using the various representations that we have done, i.e. the dashed wedge, the fissure, and of course don't forget we also did the Newman. So let's look at these 3 projections here. This is the dashed wedge. So these atoms here are in the plane. This is in front and the white is in the back. This is in front and that's in the back. So that's your dashed wedge representation. Here is the Newman. So you're looking right down this carbon and there's a carbon behind. So what you see for the same molecule is an atom here, an atom here, and an atom here. and directly behind is a carbon that has an atom here and an atom here and an atom here. We call that the eclipsed conformation. Don't forget that, the eclipsed conformation. You take that same conformation and rotate it slightly, and you have over here the Fisher projection. So notice this carbon here and this carbon here are on the same plane. This is in front, that's in front, this is in front, this is in front, red, and in the back, which is the vertical, we have the yellow and the yellow. So again, build your model. You may want to pause the video and build your model here with these colors and rotate it so you get the eclipsed, and orient the molecule in 3 different ways. The dashed wedge, here we have the Newman, and over here we have the Fisher. Same molecule, but different ways of looking at it. Of course, you know where we're going from here. We can't take pictures of molecules, just too hard and too cumbersome. So we have different representations as shown here. So let's look at this. So now we have the Fisher. So this is in front, in front, in front, in front, and in the back, and in the back. So that's an eclipse conformer. The same molecule in the dashed wedge as we had before. This is in front, in the back, in front, in the back. And this is the Newman, looking directly down a carbon to get the eclipsed conformer. So again, so this is why we need to get a good visual in 3D using your model, because this is how we will, as chemists, communicate. We will communicate using either the Fisher, the dashed wedged, or the Newman projection. And notice we have 2 chiral carbons. Here's one and here's another. Remember, a chiral carbon has 4 different groups. So here's one group, here's another group, here's another group, and here is a 4th group bonded to this carbon. And of course you can do the absolute assignment, which is the R and S. And what you should get here is that this carbon here is S, and this carbon here, which is another chiral carbon, is S. Same here. Okay, this one is a little trickier though. Okay, let us look now at relationships that are possible with these molecules. So let's build this molecule. You build this molecule using your model set. We have a bromine on this chiral carbon and a chlorine on the other chiral carbon. Okay, the way it's built here, this is an S, and this carbon here is an S. So it's 2S3S2 bromo 3 chlorobutane. Butane because there's 4 carbons, 1, 2, 3, and 4. This is another molecule, if you can imagine a mirror right down here. So this molecule here is its mirror image, because the bromine right across from each other, hydrogen right across from each other, methyl, methyl, hydrogen, hydrogen in the back, and from opposite sides, and chlorine on from the opposite sides. So these are called enantiomers because they are mirror images of each other. Even though they have 2 chiral centers, they are still enantiomers because they are mirror images of each other. Here's another trick. They are enantiomers because this is R, and this is S, pardon me, and this is R. This is S, and this is R. So they are opposites. So therefore they are enantiomers. Same applies over here, the last 2. This is a mirror. Just imagine a mirror right down here. And this molecule reflects on this molecule, therefore they are enantiomers. This is S. If you do the absolute assignment, that's S. If you do the absolute assignment here, that's R. And this is R. And this is S. Since they are opposite, they are in fact enantiomers. The question now becomes, if you should in fact compare this molecule here that I'm highlighting or circling in red with this molecule here, what's the relationship? We know they are not enantiomers because they're not mirror images of each other. And the absolute assignment, or R and S, they are not opposite. This is R, and this is S and R. So they're not enantiomers. They're not the same, because you can try this. If you try to superimpose them, they will not superimpose. All the atoms will not overlap. So try to visualize that, or even try to build it in using your model set and see it. They are not enantiomers, and they are not the same. We have a special term for that. They are called diastereomers. So they are diastereomers. Don't forget that word. That's a new term for us. Diastereomers. Okay, so diastereomers are stereoisomers that have more than one chiral carbon. They are not mirror images of each other, and they are non-superimposable. Okay, so they are stereoisomers, but they're not enantiomers, and they're not mirror images. So therefore they are diastereomers. So, conclusion. If you have here, let me see if I can get a different color here. Let's use green. So if you have this molecule here and this molecule here, the question is, what is the relationship? You can tell because this is S and S. This is R and S. So they're not opposites. They're not opposites. So therefore they are not enantiomers. And therefore they're not mirror images of each other. You can try to look across from each other. You can see that they are not mirror images. And of course they do not superimpose. So therefore they are diastereomers. Okay, so you know what's coming. Given this molecule, which has two chiral carbons, notice here's one and here's another. Why is it chiral? Why is each carbon chiral? Because it has 4 different groups. 1, 2, 3, and 4 for this carbon. And this carbon has 1, 2, 3, and 4 different groups. But this is the dashed wedge representation. And this is, of course, as you know, the Newman. And this is the eclipsed Newman. So the question now is, are they the same? Are they enantiomers? Or are they diastereomers? That becomes a very tricky question. So you'd have to deduce a way to come up with your answer. Granted, you can use your model and try to build it and see if they superimpose or what. And that's good for starters, but based on what you've seen from the model, you'll have to develop a way of analyzing that 3-dimensional picture in your brain so that when you put it on 2D screen, you can carry out the same analysis. And as I mentioned earlier, that's an important aspect of your development as a scientist because a lot of professions involve working in 3D space, but you're performing that work by looking at a 2D screen. So the better you can develop that aspect of your brain, the earlier you can do that, the better off you'll be as a scientist later on. So what happens here is you should determine that was an R, that's an S, and that's an S. You can determine that this front carbon is an S, and the back carbon is an S. So because they are SSSS, they are the same molecule, and they're not enantiomers, and they're not diastereomers. So you know what's coming on the quiz and on the exam. Quite a few of these. For you to determine as quickly as possible. Of course, for the quiz, not as quickly, you have time, but especially for the exam, you should have by then developed that aspect of your thinking so you can quickly look at a molecule and compare it to another molecule and determine if they are the same, if they are enantiomers, or are they diastereomers. Okay, let us look at this. Same type analysis, but here we have a chiral carbon that has bromine and a chiral carbon here that has bromine. Still has 4 different groups because this chiral carbon here has a bromine, a methyl, a hydrogen, and all of this group. And this chiral carbon here has a methyl, a hydrogen, a bromine, and all of that group. So each carbon there in the middle is chiral. So therefore, we can assign R and S. If you do the R and S assignment, you will get an S for this chiral carbon and an S for this chiral carbon. The same molecule, a molecule that has the same atomic attachments is shown here, where we have here the chiral carbon here and the chiral carbon here. But look at this. If you look right down here, if you treat that as a mirror, it's a mirror image of each other, or they are mirror images of each other. So therefore, they are enantiomers. Another way of looking at it is this is S and S, and this is R and R. They're opposites. So therefore, they are enantiomers. They're not diastereomers, and they're not the same. They are enantiomers. Same over here. Put a mirror right down here, you will discover that this is they're mirror images of each other. And you will discover that this is an S, and this is an R, this is an R, and that's an S. So that looks as if they would be enantiomers. Notice, looks as if they would be enantiomers. But you will recall one of the criterion that we mentioned in determining enantiomers is if there is a plane of symmetry. If there is a plane of symmetry where one half of the molecule reflects on the other half, if you have a plane going right through the middle, then it's not a molecule in which the mirror image is different from the original. So this one here shows it a little better. So here's the mirror image right down the middle, and this half reflects on that half. The other molecule here is a mirror plane right down the middle, where this half here reflects on this half. Hope you can see that. So therefore they are the same molecule, and we describe that as meso compounds. So meso compound is one where there are chiral centers in the molecule, but there is a plane of symmetry. So let's go back here for a second. So hope you can see that is that this molecule here has a plane of symmetry right down here, where this half reflects on that half, and right down here where this half reflects on that half. So even though these molecules contain here a chiral center and a chiral center and a chiral center here, they have a plane of symmetry, so therefore they are not enantiomers, and specifically they are called meso compound. So meso compound has chiral carbon, but they also have a plane of symmetry. Okay, let's look at a cyclic molecule. So here's a cyclic molecule. Hope you can see that this carbon here is chiral. Okay, so that's 1, 2. This group is different from that group. So therefore that's a chiral center or a stereogenic center. But there is a plane of symmetry right through here. And that makes it a meso compound. The other compound where there's a trans relationship, if you put a plane right down the middle here, this half does not reflect on that half. So therefore that trans is not a meso compound. So let's do that again. So a plane going right through the middle here, this half reflects on that half, of course, as you can see here. So therefore that is a meso compound. Why a meso compound? Because it has stereogenic carbons here and here, but it has a plane of symmetry. This compound over here is not a meso compound because it does not contain a plane of symmetry. Let's look at properties of stereogenic compounds. So stereogenic compounds, as we have seen, they look pretty much the same. They look pretty much the same. If you went in the lab and you had a pair of enantiomers, all the properties would be the same. That is, the color, physical properties, the color would be the same, the boiling point of that liquid would be the same, the melting point of these two liquids would be the same. The only difference is the direction in which it rotates polarized light. Polarized light is light in which the waves vibrate in one plane. Okay, so all the other planes have been filtered out. So if you get a special filter, you can filter the planes of regular light, and you get polarized light, which is light vibrating in one plane. Okay, if you pass polarized light through an enantiomer, it will rotate that light either to the right or to the left. Okay, so one enantiomer will rotate it to the right. Its enantiomer, the other enantiomer, will rotate it to the left by the same degree. So this was done very early and on glyceraldehyde. And you can see here a plus means rotating to the right, so we usually assign a plus here. And D-glyceraldehyde is to the right with the OH here. But the main thing here is that the plus is to the right, and of course the negative is to the left. That is strictly for the direction in which polarized light is rotated based on this. Here is the degree, so it's plus 8.7 degree. And over here it's minus. So notice it's minus, opposite directions. So once again, this is experimental. This is experimental. I need to point that out. This is done experimental. It is the only property of enantiomers that are different. The direction in which it rotates polarized light. You get a polarimeter. You can go in the lab and measure one enantiomer over the other enantiomer. As we have discussed before, the absolute assignment, the R and S, is an absolute arbitrary assignment. Okay, so we can still assign R and S to this carbon, and we can assign R and S to this carbon. So there's no real direct relationship between R and S assignment and the direction in which the enantiomer rotates polarized light. Okay, just some terms before we conclude or go on. A chiral carbon, same as stereogenic carbon, a carbon that has 4 different, keyword here is different groups on a carbon. Enantiomer is a non-superimposable stereoisomers, or non-superimposable stereoisomers. They're also mirror images of each other. Asymmetric compound, molecules that do not have a plane. Asymmetric, A means that it does not have a plane. Symmetric, of course, would have a plane of symmetry. Here's the term that we just covered, optically active. An optically active molecule will rotate the plane of polarized light. An optically active molecule will rotate the plane of polarized light, hence the name, optically active. So enantiomers are optically active. So note, these terms are all synonyms. Chiral molecule, optically active molecule, asymmetric molecule, stereogenic molecules are all the same. So look out for those words whenever you read your questions on the quiz or on the test. Okay, let us look now at separating enantiomers. As I mentioned earlier, in the pharmaceutical industry, they have to make sure that one enantiomer is just about 99% pure and not any of the other enantiomer possible, because as I mentioned, there are adverse effects if you have the wrong enantiomer or ingested the wrong enantiomer. So let's just see how we can separate them. One method is, let's say we have here carboxylic acids. They're a mixture of R and S carboxylic acid. Here's a chiral carbon, here's a chiral carbon. So these are enantiomers. React this with a chiral alcohol. So here's a chiral carbon, and here's a methyl group and an ethyl group, and of course there is a hydrogen in the back. This reaction here produces what's called an ester, as you have seen before. But the bottom line is this molecule here has a chiral carbon here and a chiral carbon here. So it has two chiral carbons. Here, this molecule also has two chiral carbons. Notice that this absolute assignment is the same as that, but this is different from that. So therefore, they are not enantiomers, they are diastereomers. Now key, diastereomers have different properties. They have different melting points, they have different boiling points, sometimes they have different colors, different physical properties. So we can separate diastereomers just like we separate two different compounds by some physical means. I know, chromatography, for example. Separate them out, you have two beakers of these diastereomers, 1 and 2. So now you have two separate diastereomers. Now all you need to do is to convert them back to the carboxylic acid. So if you perform a reaction here, and later on we'll study that, where we can break the ester bond right here to give back our alcohol and our carboxylic acid, and the same for this one, break the bond here, giving our alcohol and our carboxylic acid here. We have now separated out our enantiomers into two vessels. So that's the way one method of separating out enantiomers, by converting it to diastereomers, taking advantage of the different properties of diastereomers and converting it back to enantiomers. Conclusion is just some slides here, some terms. So once again, chiral carbon, same as stereogenic carbon, has 4 different groups. Enantiomers, non-superimposable mirror images of each other. Asymmetric, that means that there is not a plane of symmetry. Asymmetric. Symmetric molecules have a plane of symmetry and are achiral. Achiral. If it has more than one chiral centers in it, then we call that a meso compound. Optically active, that means that it will rotate the plane of polarized light. So that's another term that's used for enantiomers, optically active molecules. And then we looked at diastereomers. Diastereomers here are stereoisomers that have 2 or more chiral atoms, mostly carbons, and are not mirror images of each other. Keyword, not mirror image of each other, because if they were, they would be enantiomers. So they're not, but they have optically, they have in fact chiral centers. And of course, as we said, a meso compound is, meso molecules are molecules with chiral centers, but they have a plane of symmetry. Hence, they're optically inactive. So this is the last slide, I think. Yes, it is, for Chapter 5, Stereochemistry. So again, with this information and reading in your textbook, make sure again that you use your model sets as you read along and build it. Make sure you see it. Make sure you can manipulate it and visualize that manipulation, so that when you get the Fisher projection or the dashed wedge projection or the Newman projection written in 2D, you can carry out a similar manipulation and answer the questions. So continue to study hard, and again, you'll have a quiz this coming Thursday on Chapter 5. Okay?